Good afternoon, everybody, and thank you for joining us on the Survey and Spatial Lease Adjustment Squares presentation. Our presenter today is Bruce Robinson from Global Survey, and I'm sure a number of you would know Bruce. As you'll all be aware, if you do have any questions for Bruce after his presentation, we'll read all of those questions out for Bruce to answer for you. You can pop the questions into the Slido box and I'll read them out at the close of the presentation. So I'd now like to hand over to Bruce.
Thanks, Jenny. Thanks for attending, everybody. For the next 20 minutes or so, I'm actually not going to tell you how to process a least squares adjustment, but rather the process you need to go through to make sure you have a successful least squares adjustment. So let's kick into this. Dr. Paul Dennis from Otago University said there are two purposes behind this purpose of running a least squares adjustment. The first is to obtain a unique solution for a set of observations, and the second is to obtain an estimation of the position of these observations. And this is achieved by minimizing the square of the residuals. Note here, Paul does not say that you'll get a correct solution, only a unique solution. So if we have a little bit of think about what this unique solution is about, what it means is it shouldn't matter what software you're processing, Magnet, Neo, ListCAD, 12D, Snap, TVC, Infinity, StarNet, they all have least squares adjustment modules. Shouldn't matter what one of those programs you use, that you should get the same result as long as you use the same parameters and the same observations. Point to note here is that word parameters. If you don't use the same parameters, you'll get a different unique result. And the parameters that you enter into your least squares adjustment are really quite important. And so what a good part of today is to understand what those parameters are and why we enter them and the effects that they have on the results that you're going to get. What I'm not going to talk too much about is first redundancy, secondly your instrumentation, or thirdly your software. But you need redundancy in your observations. You need a good knowledge of the accuracy of your hardware used in the survey, and that doesn't just depend on your instrumentation, it also depends on if you're using total stations, on your prisms, if you're using a level, on your staves, if you're using GNSS, it could be on your tribrax. All these we need a good understanding of that so we can ensure that we get our parameters entered in correctly. And thirdly, of course, you need to know how to use your software. The way I'm going to explain this to you is in two steps, really. And first of all, what we do when we do a least squares adjustment, well, this is the way I do it anyway, is that you run an inner constrained adjustment. And the way I like to think about an inner constrained adjustment is this is where you close your own observations. This is where you're very comfortable that if you're, for example, comparing it to a Travis, is that your own data set closes within itself and that you're feeling very comfortable that it all fits. Once we've got our inner constrained adjustment working in least squares, then we go and add our control marks in, and then we can process with our control marks. And then what this enables us to do is separate those two entities, the observations and the control. I did say I wasn't going to talk too much about redundancy, but I do think it's definitely worthwhile having a quick discussion about it. In the example you can see on the screen here, we have 4 known stations. These are the triangles and 2 unknown stations. There's 16 sets of observations. There's like 2 from each station into each one of these marks. And so there's definitely redundancy in this survey. But the big question to me is when I'm presented with something like this, and I often do see people who want to do a least squares adjustment, and this is the sort of data that they present to me. The big question here is, how known are the knowns? How far apart are they? When were they surveyed? What quality were they surveyed to? And if you have confidence in all that sort of information, then an adjustment like that can work well for you. But if you don't have confidence in that, or you don't know, then to me, this is not going to produce a successful result for you. What is better is to run an adjustment like this. This is a network adjustment essentially. And you'll note actually there's only 14 observations inside here. So there's less observations than the last one. And there's 6 unknowns and no knowns. But what we can determine then is how tight our survey is within itself. This is our inner constrained. And if this is really tight, then all we are going to do afterwards is we're going to start to add in our control. And then from there, we become into our minimally constrained. So this is part 2 of the loop, if you like, adding in our control. Part 1 being back here, running our inner constraint, where all our observations are good. Okay, and we're feeling very safe and comfortable with that. And then we go through and we constrain it. Right, so the basic settings we need to enter for both the inner constrained and the constrained adjustment are, first of all, our iterations. Okay, and the iterations are how many times the process loops through. So the way least squares works is it basically gives you an estimation, uses that estimation, re-enters the data, runs it again, gives you an improved estimation, and it keeps on iterating through that process. So our parameters here, we just need to set that is what we think is a responsible number to set in here. Typically, we would have a sort of stop time as well. And in this case here, my example here, it's till the data gets to within 1 millimeter. Excuse me, I'm just going to have a quick drink here. So what this means is this would run through 5 iterations or until our residuals, our estimation of accuracy is at 1 millimeter, and it's not changing any greater than that. So, you know, if someone does a solution, runs a network adjustment or least squares adjustment using 3 iterations, and someone else uses the same survey set of data with 5 iterations, the chances are they will both get a unique solution, but they will be different. So this is one of the parameters we need to think about what we're going to use. And the key thing is here is understanding the tolerance of your survey and what you're trying to get get a reasonable result. The other thing we need to think about is what our reporting out's going to look like. And this is the confidence intervals we see. And this 95% confidence interval is pretty standard about what we want to report out. But this is when our errors are reported out to us, how confident are we that the observations are going to fall within that. And why do we choose 95%? Well, I don't know why we choose 95%, other than it's 2 standard deviations. But if we get to that, is that it's actually quite a good guide, because this is what LINs also use. So the standards for geospatial accuracy that LINs produce, they talk about 95%. So why I like to use 95% is that it actually ties in with what LINs are doing, and then that gives us a bit of an indication of how good our survey is going to be. And we can look at that, or we will look at that as we go on through the process. Back to the process. So this is my process for running our least squares adjustment. My last slide, my very, very last slide, has my email address. I'm more than happy to share this presentation with anybody who would like it. Just drop me an email and I can just send it to you. So this is the process we go through. What we want to do is we want to step through these green arrows through here. This is our inner constrained. Then we start to run our constrained, and when we're finished, we exit the process and we're done. What we don't want to be doing is being stuck in this upper loop. If we're in here removing or re-observing observations, that tells us we've got issues with our own data and we need to clean those up. Once you get through this loop, you're into the second loop, and you're coming down here to do the constrained adjustment around these points. Then it's actually what we're doing is making a decision on what control is good and what control is not so good and how we're going to manage it. It's really important that we actually do break this into these 2 sections. Comfortable with your own data, then we can get out and understand how that actually fits with the data that we've got supplied. That's our control. A big part of least squares is a statistical analysis. So it does depend how we set this up to what our results are going to look like. And just because we get a result, it doesn't mean it's a good result. So we need to be very careful in our thinking about what's going into our data. Once we start in the least squares process, one of the first tests we run is the chi-squared test. And essentially what this is going to do is it allows us to understand how accurate our data. So there's two lots of parameters we need to enter in here. Is the level of significance and the power of test. The level of significance test is also known as a type 1 error, and the power of test is also known as a type 2 error, and it's a statistical type scenario. So the level of significance is the probability of a false positive. In other words, a bad observation seen as good. Conversely, the power of test is a good observation seen as bad. You note these two don't add up to 100. They're not supposed to add up to 100. These are 80% and 5% are pretty standard numbers that you enter in. What happens if we change these? Okay, so if you change the level of significance, if you increase, by increasing that, say, to 10%, if we put this up to 10%, what you're doing is you're increasing the risk of bad observations seen as good observations. If you drop this down to like 1%, what you're actually doing is you are more likely to get type 2 errors, which is that it's good observations seen as bad. So it is a little bit of a balancing act. 5% is pretty much the standard that people seem to operate with. The power of test, I know it's not displayed in all software, and that what would, if it's not, it's probably set at 80%. And just a comment on that power of test. If you don't ensure a sufficient power, your survey may not be able to detect any true observations. And on the flip side, if you put too much power in there, it means your tests are highly sensitive to true observations, including very small ones. And this may lead to finding statistically significant results, which are provide very little use for you at all. Okay. What we're aiming for is for our chi-square test results to come out of 1. Essentially, this is actual error over predicted error. I've got an example here on the right of some observations, and we're going to look inside there and have a look at this. What I think is important to notice is the level of significance is 5%, and here it is, we'll show it down here in 5% as well. We have some bounds for that. We're going to dig into this a little bit more, but I just wanted to point out this 5% here. This 5% that is shown here has nothing to do with the 95% confidence that we're going to report out. Okay, so the level of significance is not related to that 95%. Okay. Right, so if we look at the survey a little bit closer, you will see that our upper and lower bounds are 0.913 to 1.07, and that's that 5%. This is what we're expecting our chi-square results to produce. If I look at the survey, they've observed some angles. That's at 0.5, so that fails low. Their distances, they're at 0.88, well, that fails low. Our zeniths are at 1.408, failing high. Our GPS deltas, they're at 1.2, and they're failing high. And overall, our survey is failing a little bit high. Okay, so, you know, why are they failing high or low? And this is, I think, part of the important thing to understand. Okay, so when something fails low, what it means is we've overestimated our measurement errors. Okay, and so what I mean by that is if we're putting in a total station, what we're overestimating how poorly we've observed it. We've overestimated our height and centering error, or we have errors that are correlated. If they fail high, it's typically for blunders, and probably one of the most common form of blunders that you often pick up on this is actually misnaming of points. Another reason for it to be failing high, that your centering and height errors are not accounted for at all. You have large residuals, which is typically bad observations, or we've underestimated our measurement errors. You know, and maybe here's some examples for you. You know, if it fails low, maybe it's a 1 second instrument with 3 seconds chosen as an angle parameter. Or if it's failing low for your distances, maybe it's a 1 mil EDM, you know, with 1.5 millimeters chosen. Failing high, maybe target error not accounted for. And once again, GPS delta is failing high. Maybe that your centering error is not accounted for. Or maybe there's a blunder in one or more of your observations. What's important is that this is actually a summary of all the observations, okay? It's not at each observation. You need to dig and look at all observations. So you need to check all observations, and you need to check them one at a time. Sort of my bit of a guide is the first round is you should be looking for all obs that are exceeding a cheek test of about 3. And you need to question them. Why are they 3? They miss name points, are they blunders, what's going on? You should only remove one at a time, and you rerun the process, because what we can have is correlated errors, and by removing one, you may find that actually improves others or highlights other errors as well. So the key is to remove only one at a time, unless you've got some naming blunders, which you can see pretty quickly, and you'll sort those all out. So check all observations and run and rerun. Meanwhile, we're still sitting in this upper loop going through our data. Just a note on our weights and parameters here is that increasing the standard deviations and centering and height error estimations will reduce the weight of our observations in the adjustment, okay? And therefore our adjustment is less sensitive to error detection. So it's a balancing act, okay? So we just need to make sure that we actually are having accurate estimations of our errors. A couple of things I just want to point out just to add into this. If you're using a total station, there's also a prism at the other end, and we need to make sure that is accounted for. This is super critical if you're mixing different prism types in a survey or mixing different instruments in a survey. So don't just think about the instrument, also think about the other end, what's going on. GNSS post-process data as well. We just got to be a little bit careful of that. If you look at my example here, you'll see we've observed AEE7 3 times, and the accuracy that the post-processing result is spitting out is to 0.1 of a millimetre. The question we need to ask ourselves, do we think that is actually really true? Quite possibly those 3, or the AEE7 was never moved at all when those 3 observations were taken into that set of data, and therefore, you know, there's no chance that's ever going to be wrong on top of its own position. So what we really need to think about a little bit is what our manufacturers are expecting from the results from post-process data, and we need to be adding that into the weight of the survey. Right, so you've got through the first part, you've got no blunders, you now go in and add your control points. Okay, and there can be 3 types. Really, you can add 1 point, which is, you know, minimally constrained, 2, and you get some sort of minimal constraint, or 3 or more points to keep it really super tight. Why would you add in only 1 point? Okay, so, you know, there's different reasons why you would only create 1 point. That will just get it into the right place. You need to think about what the process for the survey is. If you only add in 1 point, you can then look at your other control points and see how well they fit with the information that's supplied against them. And when I talk about this, I'm starting to talk about what our LINS tiers are and how our survey relates to that. I think this is a very good document from LINS, and it really gives us quite a good gauge of what we should expect and what LINS are using for their estimations of accuracy. Right, so iteration criteria, you know, I pointed this out right at the very start. This 1 mil, we need to be thinking if this number is relevant for our survey that we're trying to achieve. What's the goal of our least squares adjustment? You know, how accurate do we really need it? And, you know, is it fit for purpose? And this here will help us to find our iteration criteria number, but it's good to think about that in terms of those LINS tiers as well. So if I'm just going to come back a slide, we can see that they have a constant term sitting in here at the 3 mil mark. You know, if you've got a couple of first order marks, well, they're going to be no better than 3 mils anyway. And if you want to hold them against both, then maybe an iteration criteria of 1 is fair, or maybe you think it's a bit too tight and you move it out to 2 or 3. So what are our expectations? Right, so the LINS term here gives us a relative accuracy from point to point, right? So it tells us the constant term and the radius and what our expectations are at 95%. When we go through and run our least squares adjustment, what happens is we will get a confidence on the point, how accurate our point is. I'm assuming you'll know it's going to be an ellipse, and we need to look at that large side of the ellipse. What I usually do is I usually just look at the large side of the ellipse, and so that's going to be my worst case scenario. We will also get a relative confidence that comes through on our vectors between the points. So that absolute one, I'm just going to move on to the absolute. So that absolute one, like I say, is the point itself. Typically, I don't worry too much about that absolute confidence. I'm personally more interested in this relative confidence between the 2 points that we wanted to survey, or the multiple points we want to survey. Because once we have this, then what I tend to do with my data is, which I'm going to show you on the next slide, is I build a bit of a chart to understand how good my survey is going to be. And so let me just show you that now. So what I'd like to do is I would set it up something like this in Excel. And by looking at this, and I just use the long axis to pop that in there and see where the vectors agree. So from 1002 to 1000, here it is 1000 to 1000, it fails class 1. It's about class 2, but it's certainly 3, 4, or 5. Yet my vector from 1002 to 3010 fails 1, fails 2, fails 3, and is about class 4, but certainly class 5. So that gives me an indication of how good these points are starting to be and how well that network is forming. And this is one of the reasons why you may use a single point to constrain your adjustment. It's because then once again you're feeling how well it fits is within itself, and then once you've done that, maybe you go back and add another point in, and you may find that this chart actually changes, and then you're starting to get a bit of a gauge of what's going on. The last slide. Your other considerations for this process is scale. Okay, what is the purpose of the survey and what scale are we going to use? Coordinate systems. Okay, what are we going to, how's this going to affect our data set? And is the projection going to take effect? Does the deformation model come into play? If you're working on large areas over 5 kilometres, we need to start to be thinking about that deformation model. Are we going to use reduced observations or all observations? So are we going to put in every single observation we do, or are we going to reduce each set by itself and load those into the process? And are you going to recompute it every time more data is used? You may say, well, I did the survey 6 months ago and I'm feeling pretty comfortable. There's not been much change in the control, and therefore I'm going to go back and run an adjustment like I showed at the start with 4 control marks, 2 new marks, and I'm feeling very comfortable with that. Or are you going to say, well, those 2 additional marks may actually affect the way the whole network works, and I'm going to readjust my whole process or my whole network. I'm going to readjust the whole lot of it. That really depends on, once again, what the new marks' purpose are and how that affects your survey and if other marks are gone. But they do need to be considered when you go and do your adjustment. How are you going to add new marks in? If you're going to add new marks in, what's the process? What's our timeline going to be for changing and doing a full readjustment? Once you've done all that, you can save it and you can store it and you can exit the project and you're done. And that's really me done on this presentation. So like I say, there's my email address. I'm more than happy to take any questions now or at any time. Just email me and I'm happy to share the slides as well. Thank you.
Thank you so much, Bruce, and thanks for your presentation. It doesn't look like any questions have come through from any of our 200 or so participants, but if you do have any questions, can you please pop those into the Slido box now for Bruce to answer for you? Right, Bruce, we have one question that's just come through now. If the total error factor passes the CHI2 test upper lower bounds, but the observations don't, would you have to change the OBS error factors?
Yeah, so that's a really good question. So what essentially I think the question is asking, if this total value here passes, then but individuals fail, you definitely need to go back and check all the observations. The key thing here is this is just a summary. It's, if you like, I wouldn't say it's an average, but if you like, it's a guide to how the process is. You need to always check all the observations.
Thank you. Another question that's come through, what software are you using?
What software am I using? I use Infinity.
Infinity? Okay. Doesn't look like there's any other questions that have come through. What we will do, though, is we'll say to people who are on the line, if you do have any questions that pop up after this presentation, if you'd like to either flick them through to us at Survey Spatial or email them directly to Bruce, I'm sure that he would be more than happy to answer these for you. And like he has said, you're more than welcome to a copy of a copy of these PowerPoint slides. Just one last question, sorry, Bruce, it's come through. How about if the OBS errors are all low, meaning more accurate than estimated?
Okay, so I think I understand that. So in other words, well, if all the observation errors are low, then maybe some of your weighting's not quite right. Okay, so the weighting will account for that. So if they all come in low, that means if they come in low, okay, so I'm just going to come in here. If they fail low, they are failing. That means you've overestimated your errors, so you can re-enter it for those errors. You really want your actual. Sorry, I'll just come back another slide, couple slides. You really want basically your actual error over your predicted error to be right. Okay, so you want it to be 1. Failing low doesn't mean a better result. It means you've estimated your errors wrongly.
Okay, thank you. And one other question that's come through. Any comment on using one control point versus multiple when you are using GNSS observations only? Using more than one can scale/rotate the results?
So the way I always like to do it is I like to use one point, and then what I like to do is compare the other control points against my calculated coordinate of that control point and see how that fits within the LINS tier system. And I may actually even change the control point I use. Say, for example, you've got 3 other control points and they all disagree by 3 or 4 mils, just say, for example. I may then reweight it to another one and run the adjustment again, and see if the 3 that disagreed all agree nicely with themselves, and that would give me some confidence in there. So I'm happy to move them around, but that is the way I would operate with it. I just like to hold 1 or 2 fixed.
Great, thanks, Bruce. Another question that's come through. For cadastral-based adjustments where we are only interested in 2D position, does incorrect pole/instrument heights have any effect on the horizontal position, considering this is a 3D adjustment? Okay,
so most softwares you can just run a 2D adjustment as well. So no, with the caveat that if you're using GNSS, it's always a little bit dangerous with GNSS and hiding. But the short answer is no, it won't make any difference. So then your hiding error is just not relevant at all.
Okay. Sorry. Does LINS accept this sort of adjustment for cadastral data sets?
Pass. That's a good question. I'm sure they do. They do a least best adjustment for cadastral when it goes into the back end. So I'm sure there are people who are doing that, but I've never submitted a plan.
Okay, and the last question that's come through, Bruce. In your example observations, you show angles, distances, zeniths, GPS deltas. What other observations might you enter?
Okay. So what other observations may you enter? Well, it depends on what you're doing. You know, there could be a height change from levels. That's probably just about it, really. You might have directions, but most people would use angles, I would think.
Okay. Well, thank you. That was the last of the questions that came through. And as I said earlier, if there's any other questions, please feel free to email them through to us. And once again, thank you so much for your time, Bruce, for your presentation. And thank you to all of our members out there who have dialed in to listen to this live stream. Have a good day, everybody.